So today let's try to fix this huge computer power supply which was donated to me by a viewer. So thank you, and now let's try to fix it because it's broken, it's not working. And here's my cat to help me. It seems to be an ATX computer power supply with a switch here. The cable goes in here. There is some name of it. A lot of connectors here and a lot of cables. With this main connector for the motherboard and some other connectors for the peripherals, and a lot of other connectors can go here. And there is some nameplate on it with the rating 850 watts. That's quite a lot. It's a big one with a big fan. It says 80 plus. Is it like more than 80% efficiency? That's nice. And it has an active PFC, active power factor correction. And unfortunately it says do not remove this cover, so I can't open it. I'm just joking. But before opening it, let's test it. Of course, it's probably not going to work because this is the reason it was donated to me, but anyway, let's test it to see how does it behave. I have this cable and the mains, of course, and this end of it goes here, and here's a switch. Let's turn it off first, plug it in, and I have my computer power supply tester with LEDs indicating the different voltages, and also this switch simulating the signal from the motherboard to turn it from standby to active. So let's plug it in like this. And this connector is bigger, but it has just more wires for more current here. And the rest of it is the same as the smaller connector. So it's plugged in. Let's turn it on here. And the auxiliary power supply works. The red LED is the auxiliary 5 volts. And let's simulate the signal from the motherboard to wake it up. And the other voltages don't come on. So the auxiliary power supply is working. It's the 5 volt power supply. 5 volts standby. 3 amps. This is this LED, and the other voltages are not working. I can hear some strange noises from it, and I can also smell something burning from it. So this is getting interesting. Something is definitely burning in it. So let's turn it off and take a look inside. So let's remove this cover, which I'm not supposed to remove. And as you can see, the cover is not properly put on it. So it means that somebody already took a peek in it. So let's open it now. And that's it. And it opens like this. Here's the fan. And here you can see all of the circuit boards. And there's quite a lot of circuit boards in it. It's much more complex than the Chinese cheap computer power supplies. The older or cheaper or less powerful computer power supplies are just a very simple construction with just one board. Except this filter, but this one is super complex. This one seems to be very simple with just one power supply with more output. It's basically one transformer and more secondary windings just rectified and going to the outputs. And this one seems to have some special regulation for each voltage because there are some inductors probably in some buck regulators. So each voltage is probably separately regulated, instead of having just one transformer with more secondaries and just a rectification for each of them. And there seems to be a buck regulator for each voltage. A lot of semiconductors on heatsinks here. And the filter and the output board with the connectors. And there is quite a lot of inductors and transformers. This inductor is probably the interference filter, and this one is also another interference filter, and this inductor seems to be the active power factor correction. But then, what's this transformer or inductor? Of course, this is the main transformer, and this one is probably the auxiliary transformer, and this is maybe some current sensing transformer or something, but I'm not sure what's this. Here you can see probably the inductors in the buck regulators. This is probably some current sensing transformer with one turn on it. Optocouplers here, another optocoupler. So should I try to explain it or should I try to fix it? I will probably try both. And of course it's way too complex to completely reverse engineer it, but let's take a look at some interesting parts of it. Here is the interference filter with this board and this inductor and some components here. And here is the schematic of it. Here is the mains input, some class Y1 or Y2 capacitors for interference filtering, some X2 capacitors, the switch, and some inductors for filtration, a metal oxide varistor for overvoltage protection, a fuse, 15 amps, which is quite a lot, another Y1 or Y2 capacitors, and here is the bridge rectifier. And the most interesting part here is this strange 8-pin chip with resistors in series and connected just using 2 terminals. Of course, those interference filter capacitors have to be discharged when you unplug it, so you don't get a shock from the plug. And normally, you have just a discharging resistor here, but in this case it's a super high-tech system, which uses this chip, which is called an X2 capacitor discharger, and it says it's for ultra-low standby power. So it discharges those capacitors, but it doesn't draw much power when it's running. But honestly, using a special chip just to discharge those interference capacitors seems a little bit too overcomplicated to me. And the next part of it after this bridge rectifier is probably the power factor correction, an active one, which probably uses this inductor to boost the voltage. And here you can see it from the other side, and you can see quite a lot of SMD components, a lot of transistors, chips. There is a bigger chip here, a lot of 3-pin chips, 8-pin chips, transistors, some diodes. That's quite complicated, but it's nicely isolated. The isolation goes through here. It's very well isolated. And let's take a look at the power factor correction. With those capacitors after the bridge rectifier here, some current sensing resistors maybe, and the switching transistors and the power diode for the power factor correction. And there is also a relay in it. I'm not sure what it does. And this mysterious inductor or transformer. It seems to be an inductor because it has just 2 terminals connected here. And the next part after the bridge rectifier is this power factor correction or PFC. The active power factor correction is basically an electronic switching circuit which allows the power supply to draw a sine wave current from the mains. And of course you say, is this overcomplicated circuitry necessary to turn an AC voltage to a DC voltage? And of course it's not necessary. You can use just a bridge rectifier and a high capacity capacitor to turn AC to DC. But the problem with such a simple rectifier is that it doesn't draw a sine wave current from the mains. Here is the mains, and the green one is the rectified mains, and here is the voltage of the mains, and the current it draws from the mains. The capacitor charges here, and then the voltage slowly declines, and it recharges here, the voltage declines, it recharges here, and so on. And it only draws current near the peak, like this. And of course, such a distorted current waveform is not good for the mains. It puts a lot of stress on the wiring and distribution transformers and the generators in power plants and so on. This requires all of the wiring and generators and transformers to be rated for more current, because the RMS current of this is higher than the RMS current of a sine wave. When switching power supplies became common, this started to be a big problem. So there are some regulations requiring a power factor correction for high power switching power supplies. Of course, small power supplies like those USB chargers can get away with just a bridge rectifier and a capacitor because they don't draw much power, but those huge switching power supplies have to have a power factor correction like this. So in high power switching power supplies, you have to have such an overcomplicated circuitry just to turn AC voltage to DC. And of course, I didn't even draw the control circuitry. It's basically a boost regulator, but with a very low capacity at the input. Here at the input, after the bridge rectifier, there are some capacitors, but with a very low capacity, so they don't smooth the rectified sine wave of the mains. So there is basically a full ripple of the voltage at 100 or 120 Hz, double the frequency of the mains. So those capacitors don't smooth the ripple of the mains, the doubled mains frequency. They just filter the high frequency interference coming from the switching of this regulator. So at those capacitors you have a rectified mains which is not smooth. So it basically touches a zero here. And this is a boost regulator which increases the voltage. The voltage here is lower than the voltage here. So it allows the power supply to draw a current basically all the time. It can draw the current in phase with the voltage. So instead of drawing a current from the mains just when the voltage is at the peak, it allows the power supply to draw the current all the time because it's a boost regulator. It can boost the voltage. Even if the mains voltage is at a lower point than the voltage of those capacitors, it can still draw a current. And those switching transistors, probably N-channel MOSFETs, are controlled such a way that the current is in phase with the voltage. And those power transistors are controlled by some overcomplicated circuitry via this amplifier, and there is some current sensing resistor made of two resistors in parallel, and it has a very low resistance like 0.0 something ohms. And the circuitry controls those switching transistors such a way that the current is in phase with the voltage, and it uses those resistors to sense the current, of course. And here is my cat on my schematic. And there is also an NTC thermistor for inrush limitation. It reduces its resistance when it heats up, but for this super efficient power supply it probably wasn't enough, so they also put a relay in it to bypass it later. And there is also an inrush diode, which bypasses this boost regulator circuitry on inrush. When you turn it on, the inrush current goes through this diode and charges those capacitors via this NTC thermistor, and then the NTC thermistor is bypassed by this relay, and this boost regulator charges the capacitors to even higher voltage a little bit. And this diode is probably conducting only on the inrush, and then it's not passing any current. It's just a normal diode with no heatsink. And this one is an ultra-fast diode for switching applications, and it has a heatsink, and later it probably passes all of the current. So this is basically how it turns an AC voltage into a DC voltage the proper way. So it draws a sine wave current. And this bridge rectifier is here on the heatsink. Those capacitors are those brown ones. Those current sensing resistors are those big ones. Those transistors are on this heatsink and this diode as well. Those big capacitors are those. This relay is here, and the NTC thermistor is here, the green one. Here is the thermistor. Here is the inductor, probably on an iron powder core, and here is the inrush diode. So now the question is, could I fix it? And the answer is, I probably could, but it would be quite complicated. And how did I find the problem? Sometimes you can find the problem just by taking a look at it, and also by taking a look at this isolation under the board. So let's take a look at it, and You can see a big mark here on it, and also a tiny mark here. So let's take a look where it goes on the board. So this biggest mark goes to some connection on the board, which is exploded, and it's under the tiny transformer, and the other marks are under those resistors and diodes and transistors. And this small mark goes to this control chip. So here's the cat helping me, and now let's take a closer look at those exploded components. So here you can see the close-up of it, and this resistor is completely exploded. There are some other exploded resistors here. It's not readable anymore. And this diode is exploded, and a part of it is missing here. Also, this capacitor looks a little bit exploded maybe. It has some marks on it here. And here's the exploded chip with a hole in it. That's amazing. This is not going to work, and this transistor is cracked here. And also there is some exploded connection under the tiny transformer. It's the tiny transformer here. So as you can see, this power supply is properly exploded, and I could probably fix it, but it would be way too complicated, and I actually don't need it. And there can be a lot of other components which are not visibly damaged but still faulty, and this chip would be probably the hardest to get. So instead of fixing it, let's try to explain how does it work. So I have already explained the interference filter and the active PFC, which produces a high DC voltage. It's a boost regulator, so the output voltage has to be higher than the peak voltage of the highest mains voltage. So it should be at least about 340 volts, but less than 400 volts, which is the rating of those capacitors. So I guess it could be like 360 or 370 volts. So this high DC voltage goes from the PFC into the main section, which is basically a DC-DC converter, an isolated one of course, which goes from about 360 volts to 12 volts. So here is the entire schematic with my cat, which is afraid to step on it because probably it's too complicated for her. And it's basically a half bridge of power MOSFETs on this heatsink, which are switching the primary of the main transformer. And it seems like it's a frequency modulated regulation instead of a pulse width modulated regulation, because there is no inductor on the secondary side before those capacitors, and there is some resonant inductor on the primary side in series with the primary, and it's this one. And there are also some capacitors with quite a low capacity but a high voltage rating, which seems like they are not DC decoupling capacitors, they are resonant capacitors, and those are here. So this system is not regulating the voltage by changing the duty cycle. It probably runs with just a very low dead time, and it regulates the voltage by tuning the frequency. There is a resonance circuit with this inductor and those capacitors, and it can probably increase the output voltage by tuning the frequency closer to its resonant frequency, or reduce the output voltage by tuning the frequency farther from the resonant frequency. And there is the auxiliary power supply for the relay here, and the relay is this one. And those main transistors are of course switching alternately, and they are controlled by this circuitry and isolated by this gate driving transformer. So they are isolated from the control chip, which is on the secondary side. Of course it has to be isolated here because this is the primary side connected with mains, and this chip is on the secondary side connected with the output. And a positive voltage from the transformer charges the gate of the transistor via this diode and this resistor, like this. And a negative or zero voltage discharges the gate via this resistor and this PNP transistor, which amplifies the current. So it discharges the gate quite fast and also the transistor turns off fast to have lower switching losses. And the gate driving circuitry of the other transistor is the same, but the secondary of this gate driving transformer is in the other direction, so those transistors are switching alternately. When one is on, the other one is off. And the primary of this transformer is driven by some bridge of small transistors, and they are controlled by the 16-pin chip, which is exploded. So this one is exploded, this transistor is also exploded, this diode is exploded, those resistors are exploded, those ones are exploded, this diode is probably exploded as well. There is quite a lot of it exploded, and maybe those transistors are damaged as well, and even the connection to this secondary is exploded. And this transformer is this tiny one here. Or actually, the exploded one is this one. It almost looks like the isolation in this transformer failed, and the primary side got into contact with the secondary side between those windings, because there is quite a lot of damage on both sides. There are some strange marks on the pins of the transformer. It looks weird, like something metal got into the power supply, some screw fell into it and shorted it out, maybe. Here is the exploded chip, here is the bridge of the small transistors, those ones, and this transformer is here. And here is the exploded control circuitry, this one. So it really seems like it exploded for some external reason, maybe some wire getting into it, maybe some piece of wire was in the box from pin cropping and it remained here from the manufacturer and later it shorted out those pins here. Now let's take a look at the last part of this DC-DC converter, and it's this synchronous rectifier. You can basically imagine it as a normal rectifier with a double secondary and two diodes, each of them conducting in one half cycle. You can see the diodes in those transistors, and now let's pretend there are just the diodes. So when the polarity is like this one is conducting and it's charging this capacitor like this. And now this one is in reverse. And when the polarity is the other way, like this, now this one is in reverse and this one is conducting. And it's charging this capacitor like this. And those two capacitors are connected in parallel, so both half cycles go to the output. And there is an inductor for better ripple filtration. So from those capacitors it goes through this inductor and into another capacitor and then into the outputs. And there are 4 individual 12-volt outputs, and each of them has a very low resistance resistor, probably for current sensing. And for simplicity I have drawn those capacitors as individual capacitors, but in reality they are capacitor banks. And I have also drawn one transistor on each side for simplicity, but in reality they are pairs, and each of them has its own discharging resistor here, and a series resistor in series with the gate here. And here you can see the capacitor banks. 4 capacitors on some small board, and the other 4 capacitors, and after the inductor, another 3 capacitors on a small board here. And here is the inductor with just one turn, probably on an iron powder core. I initially was thinking that it's a current sensing transformer, but no, it has no secondary. So it's just an inductor, and the transistors are on this heatsink in pairs. Here you can see one pair and the other pair here. So those are the synchronous rectifier transistors here and here. Those are the transistors in the half bridge on the primary side. And the 2 parallel transistors in the active power factor correction are here, and here is the diode. You probably can't see much in it, and here you can see the screws holding them. But of course I forgot to explain this synchronous rectifier, so let's go back to it. Of course, this rectifier would work normally with just the diodes here, but the problem is that every diode has its voltage drop. A normal diode has about 1 volt voltage drop, and even a Schottky still has about half a volt voltage drop. But in super efficient power supplies, this voltage drop of a diode is a problem. Especially if the output voltage is low, every voltage drop is significant. A Schottky has about half a volt voltage drop, and there is no diode with a lower voltage drop than this at a high current. So the solution is to use a transistor instead of a diode, because a low voltage MOSFET can have a very low resistance when it's on, and this resistance will have a lower voltage drop than a diode. The transistor already has a diode in it, but when the transistor turns on, it bypasses the diode and significantly reduces the voltage drop. So the transistor basically turns on when the diode is in forward, and it turns off when it's in reverse. So it's super efficient. It has a very low voltage drop, but the disadvantage is that it's more complex, because this transistor has to be actively controlled. The gate of it has to be controlled by some control circuitry. In this case it is, or it was, the exploded chip. The transistors have to be switched according to the polarity of this secondary. One transistor has to be turned off before the polarity changes, and then, after it changes, the other one has to be turned on. So that's the main power supply, and now let's take a look at those buck regulators here, which regulate those 12 volts down to 5 volts and 3.3 volts. It seems like they are almost the same. Now let's try one experiment. I've got my computer power supply tester and I've got a 12 volt power supply, and now let's try backfeeding 12 volts into those 12 volt connectors to see what happens. And as you can see, other voltages also come on. So as you can see, the buck regulators are still working, turning the 12 volts into 5 and 3.3 volts. The buck regulators are still good. 3.3 volts here, 5 volts here. This is the 12 volt power supply, and the last LED is -12, so there is also some voltage inverter in it. So basically the main power supply is just 12 volts, and all the other voltages are generated from it later. And if I, for example, connected a 12 volt battery to this, it would generate all of the other voltages, and I could run the computer from a battery. This construction really makes it easy to add a battery backup. Also, the power good signal sometimes comes on. It's this green LED. This signal is necessary for the motherboard to start up. It tells it that the voltages are right. Now only this standby 5 volts is missing, but it could be just bridged with the normal 5 volts. And the last missing LED is this. It's -5 volts. This voltage was available in the older power supplies, but in the new ones, it's for some reason omitted. It can probably be generated from a -12 volts. As you can see in this connector, the -5 volt wire is completely missing here. So that's nice. Now can I measure the voltage coming from the active PFC? This is definitely getting dodgy. Let's put mains in it once more and plug it in. Does it explode? No. It runs somehow. Now let's measure the voltage on those main smoothing capacitors on the primary side. 381 volts. So the active PFC is still running in it. And there is one more thing. When it's in standby, the active PFC is not running. Now here you can see the mains voltage in Europe. It should be 230 and actually is 238. Now let's measure the voltage on those capacitors when it's in standby. And this is just the rectified mains. Now let's switch it into active. And now the voltage goes up because the active PFC is running. And the reason for that is that the active PFC has its own power consumption. So to have a lower standby power, in standby it doesn't run. It only runs in active. When it's in standby, only the small auxiliary power supply is running and it can run with the lower voltage. The auxiliary power supply that runs in standby has a low power, so the active PFC is not needed for it, and for a lower standby input power, it's better not to run the active PFC. It's quite a clever design made of multiple sections. The main 12-volt power supply is completely exploded, but the active PFC is still running, the auxiliary power supply is still running, the buck regulators are still running, and the voltage inverter is still running. And the power good signal, this grey wire, comes from this board, which has a chip on it which monitors all of the output voltages, and if they are good, it gives the signal to the motherboard that it can start up. And when I connect it to 12 volts, the fan also runs. It's probably temperature regulated. When it gets hotter, it runs faster. The temperature sensor seems to be on the heat sink of the Synchronous rectifier transistors. It's under this white holder. When I heat it up, the fan speeds up. And the auxiliary power supply is probably just a boring flyback, with a transformer, optocoupler here, some control chip, switching transistor, the diode on the secondary side, some capacitor, and that's it. And those buck regulators are definitely synchronous because it's a high efficiency system. They have those inductors, some capacitors, and there is the control chip in it, and some power SMD transistors. One here and another 2 transistors here, soldered onto the board. And the synchronous buck regulators work like this. It's like a normal buck regulator, but with the diode here replaced by a transistor for lower voltage drops, for the same reason as in the synchronous rectifier of the 12-volt power supply. And those transistors are controlled by the chip, and the lower transistor is actually made of 2 transistors in parallel. And this is because the output voltage is less than half of the input voltage, which means that those lower transistors are on for most of the time and they carry most of the current in average. And here is the datasheet of the chip, with some simplified schematic, pinout, the internal diagram, and an example schematic here. Now let's try to see the buck regulator on my oscilloscope. The ground of the oscilloscope goes here, one channel goes here, and the other channel goes here. So here it's on the oscilloscope. The upper trace is the output of the half bridge, and the lower trace is the gate of the lower transistors. Now let's try to zoom it out or in. And as you can see, the upper transistor turns off, and shortly after this, the lower transistor turns on. And when the lower transistor turns off, the upper transistor turns on. And the time base is 1 microsecond per division, and the signal is about slightly over 6 divisions, which is about 160 kHz. And the sensitivity of both channels is 0.5 volts per division, but the probes are times 10, so it's 5 volts per division. And you can see it's about 2.5 divisions, so it's about 12.5 volts. And this is roughly the input voltage. And here you can see the output waveform of the half bridge, and when the upper transistor turns off, there is an overshoot here, and this is because of the voltage drop of the diode in the lower transistor. But then the transistor turns on and bypasses the diode, so it drops almost no voltage here. And then the lower transistor turns off, so you can see the voltage drop of the diode again, and then the upper transistor turns back on. So there is basically some dead time. One transistor turns off, and then, after some delay, the other transistor turns on. This is to ensure that one transistor is off before the other one turns on, so there is no short circuit. And here you can see the voltage inverter generating minus 12 volts. The minus 12 volt output is this blue wire. It has some capacitors at the output. It uses this inductor on an iron powder core probably, and it uses this chip and this Schottky diode. And here you can see the simplified schematic of it. There is some capacitor at the input, at the output, there is a Schottky diode, an inductor and the chip, which probably contains some switching transistor inside of it like this. The chip is APW7174, and for simplicity, I didn't draw the rest of the circuit like the oscillator and the feedback. And the voltage inverter is quite simple. When this transistor is on, the current goes through the inductor like this, and the voltage on it has this polarity and the current is in this direction, and then the transistor turns off, and the current still goes the same direction through the inductor, but the voltage has the other polarity and the current goes like this, and it charges this capacitor to a negative voltage. And it all repeats. The transistor basically switches at a high frequency, and when it's on, it puts some energy into the inductor, and this energy is stored in it as a magnetic field in its core. And then, when the transistor turns off, this energy from the inductor charges this capacitor. So this is the voltage inverter, and this one has a normal diode in it, so it's not synchronous, but it's not necessary to make it synchronous because this one is just for a low current, just half an amp. It's low power, so the efficiency is not that critical, but in the buck regulators the current is quite high. They are rated 24 amps, so they have to be synchronous for efficiency. As well as the main 12 volt power supply, which is rated 70 amps. Now let's try to do some experiment with the active PFC. Let's try to load it. The original 12 volt power supply doesn't work anymore, so let's load it using lamps. TU in series because it's quite a high voltage, 380 volts. This is dodgy. Let's try to turn it on. Does it explode? No, it doesn't. When it's in standby, the voltage is just a rectified mains. But when it's active, it gets brighter. It's 380 volts. The active PFC only runs in active. Now let's try to sense the waveform on this active PFC inductor by putting one turn of a wire through it like this. I twisted it for less stray inductance and connected my scope to it. And here you can see the waveform. It looks strange, but it kind of makes sense. You can see a rectified mains in it, kind of, and it's basically boosting a variable voltage to a constant voltage. It works with a variable input voltage, but the output voltage has to be almost constant. The waveform of the high frequency switching is constantly changing, but you can see a constant swing in it, which indicates a constant output voltage of a boost regulator. Now it's 2 milliseconds per division, and you can see 2 half cycles of mains in it, and when I set it to high frequency, you can see very strange things in it, because the high frequency waveform is constantly changing. It's dynamically changing according to the voltage of mains. That's a black magic. And when it's in standby, it's not switching. So this is the black magic of an active PFC. Now it's 5 microseconds per division. Now 2 microseconds per division, and the period is about 8.5 divisions, which is about 17 microseconds, which means about 60 kilohertz. And the main control chip, the exploded one, is probably CM6900 or CM6901. But the last digit is not visible because of the explosion, but those two types are quite similar. You can find its datasheet yourself. It's basically a resonant controller. It can regulate the power by shifting the frequency towards the resonance, but at a very light load, it also uses pulse width modulation. And the transistors in the Synchronous rectifier are 041N, 04N, rated 40 volts, 70 amps, and the on-state resistance is 4.1 milliohms maximum. And there are 2 parallel pairs, so the resistance in parallel is 2.05 milliohms. And the maximum possible voltage drop of it is the resistance 0.00205 ohms times the maximum current of the 12 volt output, 70 amps, and the maximum voltage drop is 0.143 volts, compared to about half a volt in a Schottky diode. But at a lower current, the MOSFETs are even better because if you, for example, halve the current, the voltage drop also halves. But if you halve the current of a Schottky diode or any other diode, the voltage drop remains almost the same. And here you can see the marking of the relay. And here is the marking of the inductor and the big capacitors. And here is the tiny gate driving transformer, the huge transformer, and the auxiliary power supply flyback transformer. So this is Wild, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support. And I also have some other power supplies donated by viewers, so thank you, and of course I also plan to take a look at them.